SpaceX's Starship rocket is currently in development, with test flights being conducted from Starbase, Texas. Starship and its first stage booster Superheavy are designed to be fully and rapidly reusable, further expanding on the reuse capabilities achieved with SpaceX's Falcon 9 rocket. Designing a rapidly reusable spacecraft is a complex engineering problem that involves balancing many design trade-offs. As SpaceX has iterated on the design, some parts have been removed in pursuit of improved efficiency, most notably the landing legs on the Superheavy booster. So you might wonder how they plan to reuse the booster if it doesn't have landing legs. Well, SpaceX intends to catch the largest rocket booster ever built after it returns to the launch site with mechanical arms attached to a tower they have named Mechazilla. It sounds like science fiction, but this is exactly what SpaceX plans to do on the fifth test flight of Starship. Since the idea of catching the Superheavy booster was proposed, many have criticized it as impossible, similar to Falcon 9 booster reuse before that became routine. Over the past 5 years, I've observed the Starship program develop from welding intents to the infrastructure that we see today, and I've created many detailed 3D models of both the vehicles and ground support systems, many of which have been used by content creators all over the world to aid public understanding. With this knowledge, I want to offer up my thoughts on how the seemingly impossible feat of catching the Superheavy booster may be accomplished, and how it might be simpler than many people realize. Before explaining my interpretation of the catch process, I first need to go over design details that are important for the catching process, incorporated into both the Mechazilla launch tower and the Superheavy booster. After that, I will explain how these systems operate and the limitations and risks involved, and finally, follow up with a detailed description of how I expect the catch to occur procedurally, using all of the information presented in this video. To date, the Mechazilla catch arms have only been used to slowly lift and translate Starships and Superheavy boosters onto the orbital launch mount for testing and launches. Catching a booster will require the arms to move much faster than that required for stacking. SpaceX has upgraded both of the large pistons that move the arms to increase their movement speed, but this has come with some cost. The roughly 100-ton arms have a lot of inertia when moved at speed, resulting in a noticeable amount of sway when coming to a stop. Additionally, the hydraulic systems responsible for moving the arms at speed seems to pulse at times. The combination of these factors could make stopping the arms at a precise position for catching difficult. Keep this in mind because it will be important later. The catch arms system consists of two main components: the catch arms themselves and the carriage they are mounted to, which allows the arms to move up and down the tower. The carriage wraps around the tower and attaches using 12 skates separated into 3 pairs on both the top and bottom frames of the carriage. These skates contain an array of linear bearings that ride along the rails located on opposite sides of 3 of the tower's structural columns. Together, all 12 act like wheels on a roller coaster, constraining the carriage's motion along the length of the tower. Hardware mounted to the frame on the carriage consists of hydraulic systems and electronics responsible for controlling the large pistons that move the catch arms back and forth and actuate the smaller hydraulic systems on each arm. Each arm is attached to the carriage at 2 pivot joints. Both arms share 2 large steel pins at the lower and upper pivot joints to secure them to the carriage. The upper pin also doubles as the attachment point for the steel cable, which moves the catch arms and carriage assembly up and down the tower. The catch arms feature many systems, but the raisable landing rails are the most important for catching operations. These rails create a flat surface nearly half a meter wide and 20 meters long for the booster's load points to land on during a catch attempt. The landing rails are attached via parallel motion linkages, with some of these linkages having linear position sensors providing motion data. Under the rail near the middle are 2 pistons that can push it up nearly a meter, and once mass is placed on top, these pistons can provide downward motion control. There are also several gas springs located under the rail, which will help control the rate at which the rail lowers when mass is placed on top. Mounted to the inside face of each landing rail are an array of foam cushions encased in thin metal that protects them from the booster's exhaust plume during launch and catching operations. These pads are a specific thickness and are designed to deform and absorb kinetic energy when contacting the booster. Due to the heavy catch arms hanging off the corner of the carriage assembly, the center of mass of the assembly is not within the footprint of the tower structure. This means there's uneven loading across the 12 skates due to the constant torque being applied. When SpaceX lifts vehicles, the center of mass shifts further away from the tower footprint due to the additional mass placed around the midpoint on the arms. This can lead to binding, so the carriage has some play in the skates, but this also has some adverse effects. During catch testing, it was observed that moving the catch arms at speed or contacting an object would cause enough weight transfer to rock the catch arms and carriage assembly back and forth on the skates, producing a bouncing motion throughout the entire assembly. Due to the issues this may cause during a catch attempt, SpaceX has installed guides that further limit the motion of the carriage when raised to specific heights on the tower. These guides are located in specific areas at the expected catch height on the tower and press against the skates to further constrain their motion. They have also added additional supports to the carriage frame to increase rigidity. The combination of the guides and additional supports should help minimize flexing and movement, which causes the bouncing. Now let's talk about the Superheavy booster, which features a few key details that are important for catching. The booster will be caught using the same hardware that's used to lift the vehicle onto the launch mount. There are two small arms located on either side of the booster, and they are designed to hold the weight of the vehicle. Due to this, I call them the load points. These load points have two parts to them, an arm portion that passes through the reinforced forward section and connects to the top of the methane tank, and a cylinder that hangs below the arm. These cylinders rest on the landing rails during vehicle lifts and will also make contact with the landing rails during a catch. While these cylinders may look small, they are about 17 centimeters in diameter. They also feature a ball joint connection, allowing them to pivot independently from the rest of the booster. This ensures that the load points can make uniform contact with the landing rails even if the booster or landing rail is slightly tilted during a catch. Stringers are placed uniformly around the forward section of the booster, but below the load points there are tapered extensions to the stringers which provide a smooth transition from the tank wall to the stringer reinforced forward section. Due to their purpose and shape, I refer to these components as the stringer ramps. SpaceX has also added additional stringer ramps around the lower stabilization points, allowing a smooth transition over this hardware in case the arms close around the booster before the stabilization points have descended below the arms during a catch attempt. When Superheavy Booster 12 was rolled out recently, it was noticed that some of this hardware was covered with a black coating, possibly paint. It is believed that any markings left on the coating after a successful catch attempt will allow SpaceX to analyze the contact between the booster and the tower arms. This coating could also help minimize metal-on-metal contact during the catch attempt. Due to this new information coming late into this video's production, the following animations will exclude some of these details, but for the most part, they are supplemental and not core to the concepts that will be explained. Returning the Superheavy booster to the launch site for recovery introduces many risks. As 70 meters tall and filled with pressurized flammable gases, the booster has the potential to do some serious damage if it experiences a rapid unscheduled disassembly near critical infrastructure. Since the booster's design requires returning the booster to the launch tower instead of a neighboring landing pad, this introduces increased risk to the launch infrastructure. To prevent stating the obvious, I'll ignore extreme cases and only focus on risks associated with the booster coming down within the margin of error for a catch. One of the biggest risks during a nominal catch attempt is the potential for the booster to be off target slightly from the intended catching position. Due to this, the catch arms can't just go to a scripted spot as the booster approaches. Instead, their position will need to be flexible and be able to dynamically adjust to the booster's position, which could add a potential failure point. Another risk, which builds off the positioning error, is if the load points on the booster miss the landing rails on the catch arms while descending. This could be due to timing errors and the arms not closing in time, or the booster being rotated so much during the final stages of descent that its load points can't contact the landing rails. Additional risks include higher than expected touchdown velocity and insufficient deceleration during the landing burn. Increased touchdown velocity could cause severe damage to the booster and groundside infrastructure. In an extreme case, the arms could be sheared completely off the launch tower. If a large number of engines fail to ignite for the landing burn, this would prevent the booster from scrubbing off enough velocity quickly enough and result in the booster impacting the ground at a high rate of speed. Both of these situations could be caused by several engines not starting or aborting during the landing burn. Since SpaceX requires the use of the 3 center engines for the final touchdown, if any of these engines have an issue, the booster may not have enough thrust control to softly contact the landing rails. This would result in something similar to what happened with SN10 during its landing attempt. To minimize these risks, SpaceX will need to initially point the booster away from critical infrastructure, maintain sufficient roll and throttle control, and place the arms as close as possible to the booster to ensure that if the booster does descend between the arms, it has no option but to contact the landing rails on the way down, stopping its descent. Ideally, this would mean that the catch arms move toward the booster and stop just short of contacting it. However, precisely positioning the catch arms could present another risk due to the arm sway mentioned earlier. With all that said, SpaceX seems confident with the data they have after only one successful Super Heavy soft splashdown that a successful catch attempt is possible during the next test flight of Starship. Because of this, I believe SpaceX has a plan that removes as many failure points as possible, mitigates as many risks as possible, and keeps the overall operation as simple as possible. It became clear during testing of the catch arms that SpaceX is comfortable with contacting the side of the Super Heavy booster with the arms. This, along with the fact that they have foam cushion pads on the arms, confirms my long-standing suspicion that SpaceX will intentionally hit the booster with the arms during a catch attempt. It may seem sloppy to hit the booster, but this could essentially solve 2 problems that make catching seem more difficult at face value. The first is the precision needed to stop the arms at a specific spot, and the second is the potential positioning error of the booster at the end of the landing burn. When the catch arms contact the side of the Super Heavy booster, the foam cushions on the inside faces of the landing rails will absorb some of the inertial energy and help attenuate any bouncing. Previously, I mentioned that the foam cushions are a specific thickness. This thickness ensures that if the cushions make contact with the side of the booster and deform slightly, then the offset created by the vehicle and the arm hardware places the booster's load points directly above the landing rails. Even if the catch arms are still bouncing slightly when it's time for the load points to make contact, the landing rail is wide enough that the load points should still contact somewhere on the flat surface of the rail. All the arms need to do is maintain slight pressure against the side of the booster, and this will ensure that the load points will contact the landing rails as the booster descends. From all publicly available information, we've learned that Booster 11 was very close to its landing target in the Gulf of Mexico. Buoys placed in the Gulf captured video of the booster as it slowed to a hover above the landing target. With additional refinements to the guidance and navigation, it is reasonable to assume that this accuracy could get even better on later flights. With that said, I don't think SpaceX is heavily relying on centimeter level accuracy during the landing burn to ensure that the booster is caught. They can begin closing the arms to roughly the expected landing target based on the telemetry, but only stop once contact is made with the side of the booster. If that happens, it allows the arms to adjust to the booster's position and ensures that the booster's load points will land on the landing rails, even if the booster is off target slightly. Up until this point, I've explained things assuming that the booster is rotated so that the load points are perpendicular to the catch arms, which is ideally what you'd want during a catch attempt. A common concern I hear is that the booster could be rotated along its vertical axis or roll axis, and this could cause the load points to miss the landing rails as previously mentioned. Using my highly refined 3D models, I can place some estimates on the roll margins based on different scenarios. Assuming no deformation of the foam pads, I estimate that the booster's roll margins are limited to plus or minus 9 degrees to allow the load points to still contact the flat surface of the landing rails. If we assume the foam pads deform and squish to roughly half their thickness, this margin increases to plus or minus 15 degrees. Both of these values assume that the landing rails are contacting the sides of the booster around the stringer reinforced forward section just under the booster's load points. Due to the unknown amount of deformation the foam pads can experience, it's probably safe to assume that the real-world value trends closer to the 15-degree estimate. This estimation is somewhat confirmed by the stringer ramps located below the load points on the booster. These ramps are located plus or minus 20 degrees on either side of the load points and will be in contact with the foam pads on the landing rail. Due to this contact taking place on a different arc length, the slightly larger range ensures the stringer ramps will still softly deform the foam pads on the landing rails, even if the booster is rotated to its maximum catchable rotation of 15 degrees in either direction. As you can see, the booster can be rolled quite significantly and still result in its load points contacting the landing rails. I find it highly unlikely that SpaceX would be unable to meet the roll margins required for this unless the booster was having significant thrust vector control issues. In fact, I'd be surprised if the booster's roll orientation was off more than 5 degrees from its target, since the roll axis is one of the easiest axes to control on a rocket, especially one with multiple engines. There has been a lot of speculation about the intended catch location over the past few months. Before observed testing, all we had to go off of were conflicting simulations and animations released over the past few years. We now know that the intended catch location will be over the launch mount, thanks to recent catch testing. But let's take a look into why this might be the case, since to most people, it seemingly would increase the risk to the launch infrastructure. When fully opened, the tower arms form a circular sector with roughly a 100-degree angle. In theory, the catch could take place anywhere within this sector, since both arms could rotate into position, allowing for a catch to take place. During launches, SpaceX opens the arms all the way to create distance between the Superheavy exhaust plume and the catch arms, which helps protect them from the heat and pressure waves. Due to this, we can assume that the arms will initially be opened wider than needed for a catch to mitigate any damage from the engines during the landing burn, and more importantly, allow a larger margin of error and provide room for the flared skirt of the booster to pass between the arms. Once the flared skirt and chines pass below the arms can then close to make contact with the sides of the booster. Since we know the arms need to close at least some amount, this would reduce the circular sector usable for a catch by some unknown amount. For the sake of argument, I will assume the reduction is roughly 20 degrees on each arm, which results in a new circular sector to represent the catchable area formed by a 60-degree angle. As you can see, the 60-degree circular sector limits where the booster can target for landing, but that's not the only thing we need to consider. While both catch arms have full-length 20-meter landing rails, I believe hardware added to both arms suggests that SpaceX is planning to only use a subset of the landing rail length, which would further reduce this area. The pair of pistons that will aid with downward motion control are not spaced evenly along the length of the landing rail. Instead, they are biased toward the tower, suggesting that SpaceX is likely targeting a touchdown closer to the tower if they want to split the mass of the booster evenly between the two pistons. This theory is also supported by a few other observations. The first is the armoring they have done to the top of the booster quick disconnect hood, which would see increased heating if the booster is caught closer to the tower. The second is the fact that all future towers will have shorter arms, which will require SpaceX to target this area of the landing rail anyway. Practicing tighter constraints with more forgiving hardware will increase margins of error and be beneficial for gathering data before towers with shorter arms are used. If we assume that SpaceX restricts the usable length of the landing rail to be equal on both sides of the midpoint between the pair of pistons, that further limits the catchable area. As the arms swipe from side to side, it's clear that there's barely any catchable area that doesn't cover part of the launch mount or supporting hardware. Since we know that balancing forces on the skates and carriage is already problematic, we can assume that the ideal catching location would likely be directly in line through the diagonal of the tower, as this would balance as many forces as possible. I believe this will be the location that the booster targets for a catch, with only the possible positioning error deviating from this. Since SpaceX have confirmed the catch height, we now know the engines will be approximately 40 meters above the launch mount during the final moments of the catch. Since the location of the launch mount is not in line with the corner of the tower, the ideal catch location previously mentioned would not place the booster centered above the launch mount, but instead be offset to the side slightly and expose part of the mount deck to heating from the center 3 engines at the end of the landing burn. This will be considerably less energy than the 33 engines at liftoff, and the distance between the mount deck and engines should result in a very limited amount of deck erosion, if any at all. During Starship Flight 4, around the time Superheavy Booster 11 was landing in the Gulf of Mexico, we saw SpaceX activate the water for the water-cooled steel flame deflector, and the catch arm slowly rotated into position above the launch mount. The water from the steel flame deflector cannot cool the launch mount deck or quick disconnect hood, so I don't think activating that system would provide any benefit. Let me know in the comments below if you think the water-cooled steel flame deflector will be used during the catch or not. Targeting a catch above the launch mount seems like it would be quite risky, but as we can see, even without the additional theoretical constraints I've mentioned, there really isn't an option that doesn't overlap with the launch mount while still providing a reasonable margin of error for the catch. If you consider the additional constraints, it becomes clear that a catch over the launch mount is unavoidable. Something else that I've seen debated within the community relates to possible catch abort scenarios. I want to take a few minutes and explain what I expect to see as Superheavy Booster 12 returns to the launch site for the first catch attempt. While some of this will be a bit speculative, SpaceX has hinted at some of this, and there is data to support this in the form of booster telemetry from Starship Flights 3 and 4. Factoring in Falcon 9 return to launch site trajectory also provides some additional indications. Prior to Starship Flight 5, no booster had completed a full return to launch site duration boost back burn. This was by design to keep the booster far from the coastline for public safety. Partial boost back burns were performed, but they essentially dropped the booster straight down into the Gulf of Mexico. On Starship Flight 4, we saw the addition of the hot stage ring jettison, which, like the booster, follows a similar ballistic trajectory back down towards Earth. On previous flights, it was observed that there was a noticeable shift in the booster's trajectory as it descended into the lower atmosphere. This is likely to avoid the hot staging ring as it descends uncontrollably, but it likely also serves another purpose that I'll come back to. During Starship Flight 5, we should expect to see the boost back burn duration increase, causing the booster to reach a higher apogee and arc its ballistic trajectory closer to the coastline. Like Falcon 9, the ballistic trajectory will fall short of land just in case there is a malfunction on the vehicle. Since we know SpaceX still plans to jettison the hot stage ring during Flight 5, and it is slated to impact offshore, the ballistic trajectory of the booster must be similar when jettison occurs just after boost back shutdown. I'm guessing the ballistic trajectory for both the booster and hot staging ring will be a few kilometers offshore from the launch site. At the launch site, the ground systems will perform some self-checks to ensure that they will operate properly if the booster returns for a catch attempt. As the booster begins descending through the atmosphere, it will perform some of its own self-checks. If the booster or the launch site detects any issues, the booster will enact its first abort criteria and attempt to maintain its ballistic trajectory down to the water. We now know that SpaceX also needs to send a command to the booster before the boost back burn finishes to prevent this from automatically being enacted. If this occurs, the booster will attempt the landing burn, which should lead to a soft splashdown similar to Booster 11, but much closer to land. If we assume that the booster passes its first abort criteria, it will now use its grid fins to alter the path of the vehicle, deviating from the ballistic trajectory. The grid fins will pitch the side of the booster into the airstream, which in combination with the chines and strakes will create lift, allowing the booster to glide closer to the coastline during its descent. This puts the booster on a new trajectory that moves its point of impact from offshore in the Gulf to somewhere near the launch site. I believe this is what we can see in the previous flight telemetry when the booster shifted its trajectory toward the coast slightly. As the booster descends through the lower atmosphere, the grid fins are used to control the pitch, yaw, and roll of the booster, maintaining its trajectory toward a target. Since the booster needs to return to the launch tower to be caught, its target must be close to the tower, but away from critical infrastructure in case the landing burn fails. Superheavy will initially ignite all 13 gimbaling Raptor engines and rapidly decelerate before switching to just the center 3 gimbaling engines for the remainder of the landing burn. If the booster detects that not enough engines start for the landing burn, then it will likely enact its second abort criteria and maintain falling along the current trajectory away from critical infrastructure. It would then impact the ground at speed, causing a rapid, unscheduled disassembly similar to Starship SN8. If the landing burn ignites successfully, deceleration can occur, and the booster can then perform a slight translation to put it between the catch arms above the launch mount for a catch. Looking at satellite imagery, we can assume that SpaceX will target somewhere in this area since it provides the most protection for critical infrastructure in case the booster pencil dives into the ground. SpaceX has removed the shipping container that was previously located on the peninsula here, which housed the explosive flight termination charges used for launches. They've also added shielding to the pressure relief valve assemblies on the water-cooled steel flame deflector water storage tanks. I believe both of these observations lend some credibility to a trajectory prior to the landing burn targeting either of these areas. I believe there are two main locations SpaceX may target, the first being to the east of the launch tower near where the explosives bunker used to be, and the second is to the south side of the launch tower in the sand flats. For the remainder of the animations in this video, I have chosen to animate the booster targeting the position to the south side of the tower, but both locations are equally as likely, with the only difference being the resulting translation direction. Because of the deceleration profile, limited landing burn propellant, and the distance between the tower and the Gulf, I don't think SpaceX would be able to target a location in the Gulf prior to the landing burn starting. This would require a large, inefficient horizontal translation toward the launch tower, which could create more problems than it mitigates. A booster unable to cancel its horizontal velocity would slide straight into the launch tower, likely causing more damage than impacting the ground near the tower. During the landing burn, it's far easier to control the booster if its primary focus is canceling vertical motion and any changes in horizontal motion are minimized. If something starts to go wrong once the booster has translated closer to the tower, there's likely not much that can be done. The primary issues that come to mind would be a lack of thrust vector control or a lack of thrust output. In either of these situations, the booster would not be able to reliably fly away from the tower even if it had enough propellant, and this could create a bigger issue if it instead flew towards other critical infrastructure. At that point, any damage that comes from the catch attempt would be part of the accepted risk. Returning the Superheavy booster to the launch site involves accepting some risk, but trade-offs can be balanced carefully so that the best option possible minimizes potential damage to the launch site and surrounding environment. With all of that out of the way, this is how I envision SpaceX will catch the Superheavy booster with the Mechazilla launch tower. Note that the following is my own interpretation, but it's highly informed based on all publicly available information and my own understanding of the systems detailed throughout this video. As the booster descends into the lower atmosphere, it will use its grid fins and chines to redirect its trajectory toward the coastline. Once the booster reaches the desired altitude, the landing burn will trigger, starting with the center 3 engines, quickly followed by the outer 10. Once all 13 Raptor engines are running, the booster quickly starts decelerating and begins performing a slight translation to redirect its trajectory toward the launch tower. Once enough velocity has been scrubbed, the booster will shut down the middle ring of 10 engines and continue the translation toward the tower with only the center 3 engines running. As the booster approaches the tower, telemetry data will be streaming to the ground systems, providing the estimated touchdown position and altitude. As the booster descends between the open catch arms, it will cancel any remaining horizontal velocity and maintain control of its vertical velocity. Since the booster's flared skirt and aero surfaces need to pass below the arms before they can close against the vehicle, the catch arms have to wait until the booster reaches a predetermined altitude before beginning to rotate toward the vehicle. Once the predetermined altitude is passed, the ground systems will command the tower arms to swiftly rotate to the estimated touchdown position retrieved from the booster telemetry. The catch arm movement will begin slowing until contact is made with the side of the booster and resistance is felt. The protected foam pads will deform on contact and absorb kinetic energy from the initial impact. The pads will likely contact the booster around the middle of the methane tank, and the arms will then likely squeeze to hold their position to attenuate any bouncing. The booster will continue with a slow, controlled descent while trying to keep its position and roll orientation locked. The pads on the landing rails will rub against the sides of the booster as it continues to descend. Once the booster has descended far enough, the stringer ramps will softly transition the contact of the foam pads from the methane tank onto the stringer reinforced forward section. This will also force the arms to open slightly into the ideal position under the booster's load points. The booster will then pass a predetermined altitude, which will trigger the booster's engines to begin throttling up, slowing its descent before the load points make contact with the landing rails. The rails will begin lowering at a rate determined by the combination of the damped gas spring settings, hydraulic piston pressure, and the booster engine throttle. Linear position sensors on the parallel motion linkages will detect this motion and provide feedback to the booster to determine the optimal throttle settings for softening the final stages of descent. The landing rails will slowly lower, and once they reach their resting position, the booster's engines can be shut down. At this point, the booster will be left hanging from the catch arms and safing procedures can begin. It's currently unclear if SpaceX will use the launch mount to safe the Superheavy booster after a catch. It's reasonable to assume they don't need the mount for safing procedures, since vehicles have done so in the past without the help of ground support systems. The biggest issue with using the launch mount after a catch is that the alignment pins on the launch mount are removed before launches. These pins are required to position the bottom of the booster in the center of the launch mount, so the launch clamps can be carefully positioned around the skirt of the booster. Since SpaceX has already removed the alignment pins from the launch mount prior to Flight 5, this leads me to assume that they will safe the booster in the air and then place it on a transport stand moved into position after the vehicle is safe to approach. The sequence depicted in this video contains a combination of known facts, inferences, and admittedly some speculation. Given SpaceX's commitment to attempting a booster catch this early in flight testing, I believe they have simplified this procedure as much as possible. What I've described in this video is essentially simplified to the booster getting as close to a waypoint as possible, and the tower arms doing everything they can to get as close to the booster as possible. If that occurs, and the booster falls slowly, then it should be impossible for the booster to not be caught. Many of the ideas I proposed in this video were formulated on the basis that risks must be mitigated where possible. At this moment in time, Starship only has one operational launch pad, and any damage to the infrastructure could delay the test program for many months. As potential failure points are removed, the number of risks also decreases. I believe that this catch sequence is meant to be the equivalent of a minimum viable product, meaning it will evolve over time. The sequence wouldn't work too well to catch a Starship, since contacting the vehicle with the pads would damage many of the thermal protection tiles along the sides of the ship. Hopefully this process will become more refined over time, and the change to the shorter arms will allow the movement to become more precise, leading to contacting the vehicle aggressively, if at all unnecessary. Let me know in the comments below what you think about the catch sequence I've proposed, and if SpaceX will be able to successfully catch a Super Heavy booster on the first attempt. If you are watching this after Starship Flight 5, how did it go? Was SpaceX successful? While I'm probably biased, I think SpaceX has a pretty good shot of pulling it off on the first attempt, provided that landing burn ignition goes smoothly. If you want a behind-the-scenes look at the work that goes into producing Starship content like this, consider becoming a Patreon member using the link in the description. Also, be sure to like this video and subscribe for more high-quality Starship content in the future.